Okay.
Mm-hmm.
Do you want to use a whiteboard?
Yeah, I just wanted to like start learning about it.
You're starting learning now, yes. Have you heard of special relativity?
No.
No, yes. Relativity is nowadays when they talk about relativity, we mean Einstein's relativity. So Einstein's relativity is you're going to learn Einstein's relativity. But before Einstein in physics, we use relativity all the time. That is when we use a two frame of reference. For example, if you see the bird or airplane, and the conclusion would be different. I'm talking about velocity, right? For the bus driver and for the passenger in waiting for the bus. So that is the relativity. So if you want to know the relativity, you have really need to start with Galileo's relativity first. One is Galileo, and another is Einstein. Okay, so they are talking about the relativity. Einstein's relativity is a relativity. When you talk about Einstein, the Einstein's relativity has two components. One is called the special. We are going to discuss is called the special. Another called the general, right? And the general relativity is completely theoretical. You are not going to touch in high school.
Yeah.
The general relativity is about how to reformulating. You could reformulating gravity. Gravity. You know Newton's gravity. Using Newton, basically we mentioned the Newton's gravity. Newton. This just I give some background before we go to special relativity. Newtons have the universal. You remember? Universal gravitational law, right? Do you remember? That is a force between the two objects, right? This is the mass. Do you remember the Newton's gravitational law?
G
is equal to product of these two, right?
R squared.
Yeah, R squared. And Einstein didn't like it. He said there's no gravity. Anyway, we'll stop here. So it's geometry. So this is in terms of geometry. You can probably, if you have chance in the future, you can visit. We can discuss general relativity, but certainly that is not we're going to study relativity, right? So return to these two. So what is the difference between Galileo's relativity and Einstein's special relativity? That is something we need to know.
Yeah.
One moment. That is recording. Okay, so this is let's just say, so basically we're trying to compare Einstein's special relativity and the Galileo's relativity. Okay, so talking about the relativity, basically we are talking about the two frame of reference. Okay. So let's go to the first page here. So to understand this relativity, we have to talk about two frames, frame of reference. That is first idea is called the frame of reference. In physics, we have to tell people what is reference, where the observer is, okay? Where and where the observer located, okay, is located. So any observation, you have to, any result, any phenomena, you have to specify who observed that phenomena, especially when you study the motion is located. Okay. And talking about the frame of reference, this is a frame of reference can be divided by into two. One is called inertia, and the non-inertia. Do you know the inertia now?
Yes.
So inertia means that the relative, so the relative velocity, the velocity, the relative velocity, there's the relativity now. One moment. The relative velocity. They are more different, are uniform, constant, right? Constant. Clear now? But in the non-initial, which means that the relative is not uniform. So let's just draw the two frame of reference. So this is one. That's how people draw the reference. Frame of reference. There's another. I just consider this one-dimensional motion. So we are confined to discuss one-dimensional motion, right? In other words, the object is only moved along the one axis. Can we call it X? To differentiate these two frame of reference, I use this X dash, not the first derivative, just different X. You see? This X dash doesn't mean the first derivative. It just means it is the X when it's another frame. So this is frame one, or you can call this Y as well. You can see it's Y. This is Y. This is 0 dash, and this is 0. Okay. So the observer can on either frame of reference. Can you see? This observer A. This is observer B. Okay. So if you consider the object is moving, can you see? If you consider this object is moving, it could be in the bus, could be in the train. Can you see? Let's just show you that proper diagram. Wait a minute. I will just draw a proper object. Could it be a? Can you see this? This is object. Could be the train. Could be the moving object, right? And this object were recorded. Their position will be different, isn't it? Can we draw this line here? Can we call this frame A? Can we see this frame A? Oh, by the way, the frame is moving. I have to draw the net of the. So the frame is moving at a constant velocity. All right. And the relative to A. So this is velocity. Just do some preparation. So this is velocity, right? So this velocity is relative to A. Therefore, you can imagine that this distance is V multiplied the T, because this another frame is moving. Can you see? Now let's consider this coordinate. So this is X prime. This is X. All right. Now, can you tell me what is the relation between this X and X prime? So this is two origins. This is what is the relation between X and X prime?
X prime equals X plus Y.
No, y is not changing. How? The object only moving along the x-axis. Y is not. So can I help you? So this is
Oh, then it's just equal to each other, right?
No, they're not.
Oh.
You see, this is 0. Can you see? If can we call this is object? Can you see? This object is moving, right? This object is moving, and their position measured by observer B is x prime, but its position measured by observer A would be x. Can you see this simple relation between these two coordinates? X coordinate.
Yeah.
Right? It's just simple geometry. Can you see that?
Yeah.
This is so this is VT. Can you see? This is x prime. So therefore, x prime plus VT were equal to the x. Do you agree?
Yeah.
So that is a Galileo. This is a simple relation when we study the motion of object. Okay, and this is called the Galileo relativity. And in mathematics, I think in math specialist at a certain stage, you are going to study the relative velocity. Can you see? If you do the first derivative, let's do some math now. That's equal to d. Can we just find the first derivative? Can you see? That were equal to v. Do you agree? If we call this object is c, okay, and so therefore the first term should be written as vc relative to a, right? And this one, can you tell me what is this term? X dash. What is observed? Who observes this velocity?
Oh, VA.
No, the object B.
Oh, VB.
Because B uses they use their own coordinate. Can you see? This guy cannot use B's coordinate. So this should be velocity C relative to B. Do you agree?
Yeah.
Now the third velocity can be written as B relative to A. Have you studied this formula in mathematics? It's
no.
Called, this is called the. Oh, in general, you can write this as a vector form. Can you see? CA equal to. This is 3D motion, but this is general form plus BA. Okay, so this is called relative velocity. Relative velocity formula. Okay. So this is a part of the Galileo's relativity formula. Are you sure you haven't? Have you studied the boat? So this is a river. This is a river.
I think we did in year 10.
Year 10 or not 11, no, something like that, right?
Yes.
Yeah. So the water is moving, and the boat is moving, but the observer on the back, we will see the boat move that direction. Can you see? So that is a relativity in physics, although it was taught in mathematics. Can you see? Now, what's wrong? So it's okay. It works perfect. This formula is indeed, this is the case. This is true, right? This relative velocity is very reliable in physics in our daily life. However, something changed since Einstein. They argue that this formula cannot be true. Can you see? So if the velocity is getting closer to the c, all right, and this formula is not true, you see. So v, I just stick with 1D motion. We don't want to go to general case. So I just highlighted this formula. Although we don't use it here, it's mathematics, right? You learn in year 10 or 11. So this formula, I tell you, can you see? So this this formula, if the velocity is getting closer to the c, you see, what is the c? C is a speed of light. That is a basic idea of relativity. Everything is focused on is originated from many strange ideas are originated from this fact. Can you see? If that velocity approach to that, then this velocity is this formula became wrong. Can you see? So VCB plus VBA. So this became incorrect. Why? Why is that incorrect? Because according to Einstein and also according to experimental observation, you didn't learn that part. That's called the Michelson-Morley observation in the 1896 or something, 68 or 6. It's the last few years of the 19th century. So what they observe is that, you see, this is not right. For example, if VCB equal to C, right? And then the VCA were equal to C plus this velocity, can you see? Which is larger than C. And this is not acceptable in relativity, you see? So this in relativity, so in Einstein's relativity, so this is incorrect, can you see? So this is wrong. Einstein want to fix this problem. Can you see the program, the background now? Because do you know what is wrong? According to experimental evidence, so that is it is both the experimental evidence. The one is experimental observation. Because every theory in physics must be built on observation. And that shows that the C is a constant. Okay. Measured in all no matter in all inertia frame. That is something very unusual. Frames. Wait a moment, frames of reference. Can you see? We return to this idea of a frame of reference now. Can you see? Frame of reference. It's where this anti-intuition, you see, is anti-intuition. Because how come, you see, this just implies that if you consider if there is a say there is an airplane, right? If this airplane, when the airplane fly very relatively slow, normal speed, which is compared with speed of light, very slow. Okay. And obviously, according to this formula, the relative velocity are different. Do you agree? However, if this hypothetically, if this velocity reaches to the C, according to Einstein, according to experimental observation, the velocity is the same. That is something very anti-intuition, right?
Yeah.
So that is also, and also this is also considered. So this experimental observation is also used by Einstein. So this also Einstein called the hypothesis or assumption, or they call the postulation. Same as a hypothesis, right? The same. So C is invariant, namely constant. Okay. Now, this has a profound implication for our understanding of space and time, see? Because in order to satisfy this condition, we have changed our idea, you see? So therefore, can you see, let's just return to this diagram. So this is the first diagram. So all we have discussed here is called, so this is based on this called the Galileo's. This is the Galileo's, or mean classical, right? Galileo's relativity, right? Relativity. So that is a big deal. So basically, and from now on, so therefore Einstein says that basically according to Einstein, same relation, x equal to x prime plus vt, or if you just found the reverse, can you solve the x prime? That should be, can you solve the x prime from this equation? Yes, that's right. You can follow me. That's very good. So both of them is wrong. It's wrong. Okay, see? So both of them is wrong. They must be modified. Okay. So another thing, important thing is that the time is also the absolute in Newton's Newtonian mechanics. You see, so which means that time is absolute. So what does it mean? Absolute means it's the same. Say, for example, if these two observers have two clock or watch, can you see? So their time must be the same, isn't it? Or not? This is different time. So before Einstein, nobody paid attention. So this is called the T. It's called the T. It's called the T prime. Can you see? Now in Galileo physics, we take it for granted that in Newtonian, in the classical physics, you can say in the Newtonian mechanics or classical physics, T is always equal to T prime. Can you see? That is a foundation for classical physics. But in order to satisfy Einstein's postulation, and this is wrong. Einstein says this is wrong. According to Einstein, this is wrong. Okay. So these are the this is only true. So these are valid. Let's just draw the graph. It's just a place. These ideas are valid only in the case when the velocity of any velocity, relative velocity or the object of object, is much slower than light speed, which is a huge number. You know the number, right? You know the number is a huge number, right?
Yeah.
That is a meter per second. Actually, light speed is also the fastest velocity in the universe. There's still people in physics. Still people accept this this idea. No object can travel faster than photon or light or radiation. Okay, so this is a constraint. So this is constraint. But Einstein, in order to satisfy or in order to make Einstein happy, then we have abandoned lot of idea. Okay, so that is let's consider another scenario when the velocity is approaching to, is getting close to c, or velocity is approaching to c. Okay, not equal to, because according to Einstein, this is the first argument. Second argument is that c is maximum. See, so it's any velocity is smaller than light speed. Now, one thing we have to abandon is that not only we have to do this. You see, basically according to Galileo, we have this x prime were equal to a constant. Can you see? You have to multiply the number now. Can we put the gamma here? Can you see? A factor. I will have to put a factor x minus vt. And also the time is also not constant anymore. We have put the gamma here. Can you see? We have put a gamma here. Can we just put this t here? The t. This is something I just discussed with another student yesterday. So I can write the formula here. Okay. So this is a new formula in relativity now. This is c squared. This is x. In other words, in general, t is not equal to t. In general, can you see? In general situation. So time is different now. So be sure that when you study relativity, so this is very essential formula, can you see? Now tell me, can you follow me? Both x and t have prime, which means that is measured or used by the observer B. And on the left-hand side, on the right-hand side, that is x is a coordinate used by observer A. And also they use his clock. Can you see? So that is, I think if you can understand this idea so far, then you should be able to know what you are trying to, what you can expect it to happen. One thing is certain that the time could be different. Okay.
Yeah.
For example, in this case, for example, the flower, you see, the flower could grow slower. It's very strange, isn't it? Yes.
Yeah.
You put a flower here because everything changes. Because Einstein says so. If you accept Einstein's idea, you have give up all these ideas. You see, so the flower grows slower. Can you see? So this is just a hypothetical flower. So that the flower grows flower. And on the other hand, the flower in this one would appear to grow faster. Can you see? Do you believe or not?
Not really.
You can hardly believe, right?
Yeah.
So that is a phenomenon is called the time dilation. Okay, you were going to learn two formula in relativity in the high school. This is a phenomenon is called the time dilation. It's called this phenomena. This is called the time dilation. Right down here. So this is called the time dilation. Getting longer. In other words, in this case, t is shorter than t prime. Can you see?
Yeah. So why does that? How do we know that happens? Like, why does it happen?
No, the reason you didn't follow me. We change this idea. We let the time different because we have accept this assumption or postulation that light travel at a constant speed, measured observed by any frame of reference.
Oh.
You see, that is the reason. That is just logical consequences, no reason. Yeah. Because you see, if you, in other words, and how can we find the common, can we use a simple analogy to describe the relativity? And
isn't this all just theoretical? Like you can't prove it really.
Well, actually, that is a good question. Okay, and one of the famous, I just found some analog for you. One famous is because if the people travel, one is stay at on Earth, Actually, I discussed this for phenomena in the YouTube many years ago. Did you notice I have YouTube?
No, I
No,
didn't.
doesn't matter. It's not. It's just for education purpose. YouTube. I show you that one for fun. I stopped it for time being. Okay. I trying to find that. Oh, you can help me to promote my YouTube if you wish, if you could. Anyway, I show you one of my earliest, my older YouTube. Okay, doesn't matter. It's just it's all about physics on this website. It's not for other purpose. Let's see. Where's my channel? Also, this one. There's no twin brother. That's one. Can you see?
Yeah.
This title is called the no twin paradox in Einstein's special relativity. That is my argument.
Mm-hmm.
But before this discussion, many people accept this paradox.
Yeah.
What means that when the twin, the two person, one is the same age, right? Born at the same time. If this, let's go to larger. So if this A is still on Earth, right? And another one is travel with a spaceship, go very far away at high speed. Okay. According to Einstein's time dilation, when this another twin travel back, he will find that the twin A on the Earth is getting very old.
Yeah. And
he is still young, relatively. Of course, this is in my video. I argue this is wrong. Okay, I say this is because if you don't start, so this is how I make this formula. Can you see? To explain why this is, you cannot observe this, you cannot see this phenomena, right? Also, just like that flower analog, can you see? Because when you study special relativity, you will encounter a lot of strange questions. Let's return to our discussion. So this is one of the paradox. Okay, paradox means that it's controversial or it's unsolved. Okay, it's hypothesis, kind of hypothesis. This is a thought experiment. Thought. You can't put the two brothers separated by many years in that way. No, at a very high speed, and also that I think that is the introduction to the relativity. Any question?
We're also doing some simultaneity.
Simultaneity is part of the special relativity.
I think that's what we just. Yeah.
And again, because simultaneity is true when we use the Galileo's transformation, because if we assume time is absolute, right? And every observer uses the same clock. The time is the same. So therefore, if something happens in the one frame, observed by one observe, and you can see that it's possible to determine whether the event happens simultaneously. It's called simultaneity. And this is another extreme example to using Einstein's special relativity. In short, according to Einstein's special relativity, simultaneous event is it cannot be determined because the time is different. The local time is different, and a clock is different. So that is a brief discussion. In order to explain this idea, you really have to learn what we call the Lorentz transformation. Have you heard of Lorentz transformation?
No.
Yes. So to discuss this simultaneity, this simultaneity, right?
Mhm.
This is if you want to understand that, you have to use Noreen's based on Noreen's transformation. Noreen's transformation. What is Noreen's transformation? Actually, I just make the video on Noreen's transformation. If you're interested, you can watch in the future. Up to you, right? Noreen's transformation is provided the formula. So this is a Noreen's transformation. Can you see? This formula is called the Noreen's transformation. Although we only discussed very briefly today, we actually have touched some of the basic formulas in relativity. So in this case, can you see? Oh, what I'm doing. Okay. So this formula, can you see? This is called Noreen's transformation. Why do we call this Noreen's transformation? Have you studied metrics? You studied vector. Yeah.
Yeah.
So these can be considered vector. Can you see? Can you see x prime, t prime can be written as a matrix. Do you agree? The matrix have 4 elements. Can you see A, B, C, D, or we can say A, B, F, G, up to these 4 elements. Have you studied matrix?
Yes.
Do you know how to work out this product? Do you know how to do this? So this is called the T. This is called the transformation matrix. This is called the matrix. This is called the matrix of transformation. Have you studied transformation in mathematics? Every transformation can be written as this is called the matrix. Matrix. Any transformation can be considered as written as a matrix. Matrix. So let's just continue. If you want to know more, so basically, if we just put the 2 formulas together, you tell me. Can you see? What do we have discussed today here? First is a Galileo. One is Galileo's transformation. Okay. Transformation. Another is called Noreen's transformation. Noreen's transformation. All about the relativity, but the Galileo transformation is about classical relativity, where Noreen's transformation is for Einstein's special relativity. So what is Galileo's transformation? Do you remember? Galileo's transformation can be written as x prime, t prime. Do you know what is x prime, t prime now today? What is x prime? What's t prime?
X prime is x plus vt.
Now x prime is the coordinate of the frame B. This is frame B. This is from frame B. Can you see? This is the coordinate in frame B. Oh, by the way, when you study relativity, you will consider the time as a part of space.
Yeah.
And then you multiply something. Can we just rewrite this one? Do some exercise. That is equal to x. This time is minus because you got reverse. That is minus vt. All right. And that will be just t. You see. So this is Galileo's. This is Galileo's transformation. Now, if you want to write that, can you work out these 4 elements? If you have studied the 2x2 matrix, can you work out these 4 elements here for me? Do you know what I mean?
Yeah.
I'm looking to, how about these 4 elements? Can you find these 4 elements to satisfy this equation? Oh, good. Very good. Other 2? Yes, very good. So therefore, that's very good. So for Galileo transformation, so the transformation matrix for the Galileo okay, is equal to this simple matrix 1, 1, 0, negative v. Can you see?
Yeah.
How about the inverse? You know the inverse?
Is it 1, 1, 0? Wait, I'll do it.
Yeah, that is 1 multiply 1, right? Minus 0 multiply negative v, right? That is called determinant, right? It's called determinant. Yeah. And then we have to shift that, where it became 1, 1, 0 positive v. Can you see?
Yeah.
Or is it just simply equal to 1, 1, 0 positive v. Can you see? So you can see that if you can use this formula to work. Can you use this formula? How about can you use this formula to work out the xt?
Oh, in the inverse?
Yeah, inverse. So you have to use the inverse here. Yeah. Plus, yes, that's right. And a t, right? Good. Yes, so that is so this part. So this part is a Galileo, the classical physics. Okay.
Yeah.
This is that's you need to know, because some teacher some school don't teach this background. They're starting from time dilation, simultaneity, and or twin paradox. And some they jump to that abstract conclusion idea first. But if you really want to know what is a special relativity, I think your brother spend more time than other students to learn relativity. And so basically that is a Galileo. Okay, let's return to the Lorentz transformation. Do you remember? We discussed Lorentz transformation. What is the formula? Do you remember? That is x prime t prime equal to the factor gamma, right?
Yeah.
Okay, and that would be Can you write this one? Can you work out the Lorentz transformation matrix inside the 4 element? Do you want to go back to find that structure? So these 4. What are the 4 elements here? Same question, similar question. Can we go back to see? This is Lorentz transformation. Can you see? Can we write it down for you? Lorentz transformation can we just write the Lorentz transformation down there for you? So x prime is equal to gamma, and x this time is minus vt, and the t prime is equal to gamma multiply t, take v over c squared x. Now, can you, based on these 2 equations, to work out these 4 elements, please? 1 is negative v. Oh, that you are quick. I make some trouble for you, but you solve that. I change the order. Yes, that's right. So that is you today you have learned a lot actually. So basically, from this formula, we know this transformation of Lorentz matrix. Can you see? Because L for Lorentz, right? Is equal to the gamma 1, 1. Can you see? Negative 5, negative v over c squared. Or if you want to look nicer, you just put the beta. You put the gamma factor inside. Can you see? So that is how people use the. So that is v in gamma. Can you see? C squared. But what is gamma? We don't have much time now. If I have time, I can show you what is gamma. What is gamma? What do you think?
Is it just a constant?
It is it's dependent on the velocity. Gamma is related depend on this ratio. I give you the, so gamma is the function of the V over C.
Mm-hmm.
So let's go to next one, 4. Oh, yeah, I just drew another one. We still have some time. Before you study the time dilation or simultaneity, you have to understand its background, all right? The rest, what we can do is just use this Lorentz transformation to explain the related phenomena. Okay.
Yeah.
So if you at a school, if they don't teach Lorentz transformation, they cannot solve many problems. Or you can even you cannot debate as a problem. But what I show you here is what I see that. So basically, this is gamma. We got x prime equal to gamma factor x minus Vt. So I alternately use equation or matrix. It's the same. It's equivalent. Okay. So that is the formula for this. This is a t. Take the c square x. All right. So this is Lorentz transformation. So what is the gamma? I give you the result. Have you seen this factor before? This is gamma factor. Have you seen this factor in your textbook?
No.
Oh, well, if you haven't studied, can you go to your textbook to find this formula for gamma? Do you use a textbook at all? Digital?
We do have a textbook. We just never use it.
You never use it? Oh, yes, yes, yeah. Well, the teacher is lazy. Can you show me your textbook, or is it digital one?
Yeah, it's a digital one.
Okay, can you show me text? I give you. I also look at what you're going to learn, because you don't have. There's endless ideas in special relativity. I don't think you can start it all just during the year 12. You can spend years to study Einstein's relativity. Actually, during the time of Einstein, there are only a dozen or less than 5 people or 3 understand the special Einstein's idea. Now, probably more people understand his idea now.
Yeah. So this is the special relativity chapter.
Yeah, oh, good. Yes, that's the study of Einstein's special relativity, simple matter. Yes. Why did you choose that special simultaneity words? Did you read before this chapter? Or did your teacher do some advertising?
It's on the side here, so I just
You can show me. Where's gamma fact? Can you find the gamma formula first? The gamma equal to 1 over square root.
That might be in time dilation.
Time dilation, yes. Both time dilation and also okay. Yeah, this last page. Can you enlarge the last page with formula?
Oh, here we go.
Yeah. Can you see that factor now? They're trying to. So this is the result. Can you see this result? So in this result, the one. Oh, I can't participate. Anyway, so the last formula is a gamma. Can you see this gamma factor? So that's time dilation factor. Can you see the gamma factor? Yeah, can you see the gamma now? Can you see the gamma here? So today we are using the gamma now already. So actually, what I introduced to you today is more general than the formula in your textbook. So if you wish, we can next time we can show how to prove how to derive this formula mathematically, right?
Yeah.
But up to you. If you're not interested, we'll not go that abstract idea. So at least, so what you learn today is that Einstein, the context, the background, and also the history. You see, so Einstein didn't put his idea. I can give you draw some timeline here. So if you go to the timeline here, so imagine that relativity is nothing new. So you back into the 1700s, okay? Galileo already have this idea. Galileo also have this idea that is velocity is relative. You see, velocity CA is equal to velocity CB plus velocity BA, right? A and B are frame of reference, okay? So one is A, that one is B, another is A. Can you see? So this is X, X, X prime, X, okay? But it's not until 1905. So Einstein argued that, well, before that, in the 18, you check that 1806, something like that, the microsyn. So microsyn and Monet, they have done experiment. This experiment, this experiment new in there. And they say the experiment says no ether. Do you know the ether? No ether. That is the experiment. So in other words, the wave, the electromagnetic wave travel in the space without media. So there's no media. So no media. That's called, this is called the EM wave, electromagnetic wave, right? So in 1906, Einstein put his idea. So based on this experiment, he put this idea. So this is famous formula mc squared. This is part of the special relativity. If you wish, we can show you how did he observe this formula. Otherwise, we can just simply apply it. Okay. So from here, he argues that so this but also CA is not equal to CCB plus VBC if we approach it to C. Okay. And also the change for, so here you have to use Galileo's transformation. And actually, Lorentz discovered this transformation before Einstein. This is Lorentz. He's dealing with issue in electromagnetism. So Lorentz got his idea, and Einstein simply used it. So in this case, so the transformation has been used by Lorentz. Can you see? That is very famous. Can you see? It's you can get a Nobel Prize if you did that by yourself in that period, during that period of time. Can you see?
Yeah.
So this simple formula where gamma, we have discussed a lot of things today. Gamma is 1 minus v squared divided by c squared. That's it. That is a timeline for the special relativity. It's timeline, right? Okay, I'll see you next time. What time? Friday, right?
Wednesday next week, right?
Wednesday. Okay, Wednesday for math, for the mathematics. Yes, I remember. Yeah. Okay, enjoy your study.
Thank you. Thank you.
If you are up to you, if you wish, we can go more like your brother. Otherwise, we can just focus on textbook. Okay.
Let's go more into it next time, I think.
Okay,
it'll help
good.
me understand it better.
Because you see, because your math is good. Okay, you can, if you can follow me, we can go further. Okay, up to you.